Hello, everybody. Welcome to Fastware. Today we're going to be talking about one of the most interesting topics to me, and that is memory allocation. And memory allocation is by far the most critical component to any software system, and it affects its performance quite drastically. So today we're going to be looking what else we can do to improve the performance of our applications by just replacing memory allocation. However, this topic comes with few caveats, so we'll get to them later on in the video. So today we're going to start with operator new and delete. So here I'm at CPP reference, looking at low-level memory management structures, and we have operators new and operators delete, and some explanation how to handle and overload and replace with your own. So let's have a look at operator new. And right here we have the replaceable allocation functions and replaceable non-throwing allocation functions. So there are 8 of them, and that's exactly what we'll do. We'll just grab these and put them in some CPP file, which need to be linked to your application. So that object file, as long as it's linked, these functions will be called accordingly. And as well, we have their counterparts, which are delete allocation functions, or delete functions. Obviously, where we have is 8 of them as well. I'm ignoring the throwing delete functions because that makes no sense at all. And so we have the normal delete, no except, an array delete, the same thing for delete functions with alignment, delete functions with size, and both with size and the alignment. So these are 8 functions. So I would like to demonstrate how they look, and that should be fairly straightforward. So allocation functions and delete functions. So here are all 8. So here they are. Operator new with count. This is the size to be allocated. An array version. The same with count and alignment. And that's all you pretty much have to do. You only replace them and put whatever code you want there to replace your allocation functions. Delete is exactly the same way. You just provide the operator delete with a void pointer in size, void pointer in size for arrays, and all the other one, and provide any code that you want. So today I have a little application, or it's a benchmark as always, which contain this bench object, has some member fields, unimportant what they are, unimportant what they do, and a second one with just some accumulator and as well. Very unimportant what they actually do. So the important part here is that we create a vector of the composite bench objects, the shared object of them, and then we go on and actually create a unique pointer of bench objects, and we put one inside the other, we perform some calculations. It's really nothing important here. So the critical part that we want to test is this unique, this shared, and obviously the vectors themselves, which will need to allocate memory. So as I mentioned, memory allocation is critical. And in order to understand what your application does, you want to be able to profile, see how much memory it allocates, what sizes they are, so you can start formalizing the strategy how to actually replace the existing new with something maybe a little bit better. So what I've done is to provide a little header called memory profile, which has just begin, clear, and end functions, and some type definitions which we will use later. So let's have a look how they're implemented. So here is my memory profile, my namespace, and what we have is our begin, clear, and end functions. So begin just clears out the data, clear clears the allocation data only, and the end actually prints our data set. Right? So that's very straightforward. It will tell us how many allocations of each size there were and what was the total, the maximum usage of memory in our application. So since you're replacing the new and delete functions, you cannot really use the standard containers very easily, since if you would call new from the standard container, it would loop back into your new. So if you're trying to profile any information using standard containers, what you will need to do is to provide your own custom allocators to these types. So what I'm using here is two unordered maps, which I have to provide this temp allocator, which is the way C++ 11 and upwards provide allocators. It's the template argument. And this particular allocator just implements the allocator interface, does nothing whatsoever smart, and just forwards to malloc directly and malloc and free directly. So it does nothing interesting here. You just, if you want to know how it's done, just Google allocators on CPP reference and you'll be able to figure that one out. It's not particularly complicated. So I have to use this for my unordered maps in order to collect information. As I said, otherwise you would come up in a circle where calling new would, you try to collect information, goes to unordered map calls new, goes back to the same thing, and it gets stuck in a loop. So you don't want to do that, obviously. So the first thing that you want to do is implement this printer in order to see what your application is doing and how much memory it's allocating at each size. So this is how generally it would look like. So for every new call, what we want to do is say, if memory profile we're supposed to collect data, what we want to do is just say, okay, allocator without alignment, just for that count you add that there was another alignment of that size. The current allocation size, so you want to do know how much currently how much memory currently is allocated, and the max allocation size is obviously what we will do is just do a max between the maximum allocation and the current allocation. Obviously, this is only important, the max allocation size, when you're deallocating memory, not when you're allocating, since it's always only growing. However, I just included for posterity, as it is not a production quality code and it only serves one purpose here in order to collect enough information so you know what your application is doing, right? So let's continue with that. So let me quickly build that, and what I'm going to do is just run. Now, obviously, this just starts printing and printing and printing and printing. So, one thing I forgot to tell you or show you is how it is actually being done. And here it is. So in my test, what I do is I call the memory profile begin and memory profile clear at the beginning of each iteration. And then once all iterations are done, I just call memory profile end in order to print the output that you saw there in those logs. So here are the logs. So we can see that there are 1,215 allocations of 40 bytes. We have a large number here. What is it? 3, another 3, so almost 6 million allocations of 56 bytes, and then a few more allocations which are much larger. So, step 2. So now we know how much memory is being used So here we say total unallocated size, total aligned, so total unaligned allocations, total aligned allocations. So no, we're not using any aligned allocations here. And then it says max memory usage altogether. So what we'll do now is just quickly have a look what we can do. So I have implemented a very, very trivial memory allocation. So this is the composable memory allocators, for which I can show Andre's talk. He teaches how to use these composable memory allocators and how to write them. So the API pretty much follows his recommendations, where you have the allocate owns, and you basically inherit one from another. Obviously, it's not as extensive of API because I don't need all the functions that he shows that you could implement and how to do so, because I'm only doing one thing. I'm implementing a pool allocator. And a pool allocator basically has pre-allocated pool of memory. It segments them and weaves a pointer through them. That would be like a free pool. However, I'm having a little bit more performant implementation, since I have a separate array of exactly the same size as the pool for control blocks, which are just pointer sizes, and they weave the pointer through that. So I'm keeping my metadata about allocation separate from the data, not so to avoid actually accessing cold memory when I'm freeing. So this is basically critical in order to keep your memory allocators as fast as possible, and hence I'm doing that here. So the memory pool allocator, I will include a link in a description for you to have a look at how it is actually implemented. However, it is fairly trivial. All of you are more than capable of implementing it yourselves, I'm sure of it. So let's have a look how it actually performs. So let's actually disable the printer and put our terminal in, clear this mess up. And what I'm going to do is just, I'm gonna build, as I did. So what I'm gonna do is just run using a standard new, nothing up my sleeve, this benchmark 2 seconds each to collect some information to give us the baseline to know if we're doing better or worse or equivalent, how long each of these take. And obviously, as I always profile at different scales, very few objects and goes all the way to a lot of objects. So we just collected some information on how this is done. So what I'm going to do is now I'm going to enable this standard pool allocator that I implemented. And here it is. Let me just build this. Go back to the terminal. Now run this particular implementation, and we can compare and contrast. Here, we're finally done. And now I'm gonna put all this data. So I'm gonna show you the method how I used to actually determine if I did better or worse. So what I'm gonna do is I'm gonna copy information from both of these and just dump in some spreadsheet. So here's my spreadsheet. And what I do is I just dump this information from my first run, which is using standard new, and the second run, which is using my custom allocators. I'm gonna quickly do and just replace this header with empty so I don't have to bother with it. Remove unnecessary columns as it is unnecessary. So now I just have the times. I'm gonna put them next to each other. Don't need this anymore. So as I said, this is new. I could spell. Now I could take this directly and say, okay, so let's put, okay, bar chart. Data series and columns, the yes, yes, yes. So, okay. That shows that basically the custom takes less time. Great. However, that doesn't really, I mean, I don't know, there is no data here. It's difficult to see. So what we need is to get some perspective on this data set. And the way I do that is actually align data sizes. So what I mean by that is I do a ratio, basically, because it is difficult to see at smaller scale. So I just put for my baseline 1, and for my custom, what I will do is I'll take the time new, and then I'm gonna delete it by the custom, right? And just drag it over. Format my cells, so I have 2DP. And now, when I take this, so let's use a line chart, because line chart's cool. So we take a smooth step, yes, yes. And now we have a little line chart. So here, the line chart demonstrates that the new, our baseline, so sets at 1. And here is the relative improvement with our custom allocate. So from 1.4 to about 1.6 times faster. So as you can see, you can improve your application's performance by using a custom memory allocator. However, now comes the caveat. Let's go back to our code. Now, this is our code. Let's have a look how it is implemented. And the caveat here is that each object is put in this bench object and allocated separately. Unique allocations are for every single object. This obviously is terrible because we're scattering and we're requesting memory allocations no matter how fast each of them are. We're just requesting each little object to be allocated separately, which is terrible. The object-oriented model of C++, how it is used, and this is what I was trying to follow, the code that I see all the time, this is the pattern, it's terrible for performance. No matter how fast your memory allocator is, if you're just allocating stupid little objects, or large stupid objects, directly on heap, without thinking how they're going to be used or structuring them, you can only do so good. And on my machine, it's 1.6 times on average that I can do better than a standard new allocator. My machine is AMD Threadripper. I have 16 core AMD Threadripper, and that means that there is no way to make your applications faster if you don't think about how you actually write the code. By replacing memory allocator, yes, you can do a little faster, but it's not ideal. And actually rewriting this code to be more linear, less memory allocations, would do much better than any actual allocators that you can implement. However, when you're allocating large objects, your custom memory allocators can do much, much better because malloc or new are very good at allocating small objects. And we can outperform that 1.6 times faster using custom memory allocator on that. So in the best case scenario for new, we can do better. on a large scales, on very big objects, like allocating huge arrays, actually new does much, much worse. So, and we will look at that probably sometime in the future. So with that, I think I'm done. And I hope you enjoyed this information and you found it useful. And if you did, click that like button, subscribe, leave some comments. If you disagree, agree, call me names, whatever it is, give me a shout so I know that you found it interesting, or you want to debate me on this. And with that, have a good day and take care now.